All right, Math 2, Unit 1, Section 1. So we're classifying real numbers and properties of exponents. So these are going to be two different ideas that we have here. The front page is going to be classifying numbers, and the second page is properties of exponents. So starting off here, the real number system. What we're going to do here is we're going to start at the most specific spot, the natural numbers. They're all the way in the middle. Natural numbers are like the oldest numbers that we have. It's like 1, 2, 3, and so on, right? Whenever you were very little, you probably counted 1, 2, 3, and so on. Next up, whenever you grew up a little bit, you started to count with the number 0. So you had the whole numbers, which are 0, 1, 2, 3, and so on. After you graduate from the whole numbers, you go into the integers, and integers are just what normally we call whole numbers, but they're integers. They're the negatives and the positives. So -3, -2, -1, 0, 1, 2, and so on. Then we get into rational numbers. And rational numbers is a much larger family, or much larger group. Rational number, the definition of it is that you have an a over b, where those are both integers, and b is not 0. All right. So anything that you can write as a fraction. So you could say 3/4 or 1/2. You could also say things like fractions that repeat. 6.3 repeating is a rational number, right? Because 3 repeating is 1/3, so that falls in this category. Um, we also have improper fractions, and I'll write one of those, maybe like 5/4 falls in that category as well. Those are rational numbers, all right? Rational numbers can be written as a fraction. Now we have irrational numbers, and those are numbers that aren't rational, right? Those are numbers that if you type them in your calculator, there's never going to be a repeating decimal or something like that. Some of the hallmark irrational numbers are pi, right? You type pi in and it never repeats. It never does anything fancy. It never stops. It just keeps going and going, and there's no pattern to it. Other numbers that are similar to that would be like the square root of 5 or the cubed root of 6. If you type any of those in your calculator, they're going to just keep they're going to keep on giving more decimals with no repeating. So now that we have these, we want to talk just a little bit about symbolism that's used. So we have up here the real number system, all right? So that's our biggest group, our biggest family. Everything that we've talked about so far falls into the real number system. The real number system has a symbol of a little r like that. And let me write that again so you can see it. Starting off, you put 2 lines, and then you make a P, and then you make the leg for the R. All right, and that's the real numbers. That's the symbol that means real numbers, right? We'll probably use that symbol some. The rationals also have a symbol, but it's a Q. And whenever we write it by hand, you make a Q, just a normal Q, and then you draw a straight line, normally on the little bit of the left side of it, okay? For integers, we use a Z. So you have a Z, and then you draw like an extra line next to the Z, right? And that's not super pretty there, but that's not very pretty either. Something like that. Whole numbers get a W, and then we have like extra lines on it. And then the natural numbers is a fancy N with an extra line there. The whole numbers might also be described as an N with a little 0 at the bottom, because it means like it's the naturals plus 0. So they might be described as that. The irrationals might be described with an I, and it normally looks something like, well, that's not quite right. And maybe something a whole lot like that. Okay. These look a whole lot better on the computer has a much nicer way of doing it. In fact, if you type out or if you go on Google and you say real number system symbols, it'll show you all the symbols, and they're much prettier on the computer. But this is what we'll be using here. You can either use the symbol or you can use the real word or the whole word. I don't care. But it's good to know these symbols. So, number one, it says to classify the following numbers in the most specific way possible. So we're not going to list it multiple times. We're going to just list one word, one group. Okay. So -8, where does it fall in our group? It falls in the integers, right? It does not fall in the whole numbers, so we're going to have to go integers. Integers is the most specific way. Going straight down to B, B is 0. 0 is a whole number. The cubed root of 7. If you have any kind of root, and it's not a nice, pretty root, it's going to be irrational, right? If you had the square root of 4, like in D, that's going to be well, that's equal to 2, so that's a natural number. But the cubed root of 7 is going to be irrational. All right. Moving on, number E, we have 3/8. Well, 3/8 is a fraction, and it doesn't simplify to be an integer, so it's going to be a rational number. Nine pi. Well, that's going to fall into our irrational over here because it's 9 times an irrational number. So this is going to be irrational. G, 9.387543. Well, we might want to say that's irrational, but it actually is going to be a rational number. It's not going to be an integer, but it's rational. And the reason is because it has a decimal, but the decimal terminates. The decimal ends. So this will be rational. H, we have square root of 9 over -1. Well, let's simplify that. That would be like 3 over -1, which would be -3. So that falls into the integers. All right. So that's how we do our front page. This is going to be the first side of your homework is going to be very similar to this. Make sure you have this this graph somewhere near you. It helps a lot. All right, second page. Now we have exponent rules. So over here we have the fancy wording of it. And then this piece here is actually going to be the piece that you really want to look at. And over on the right, I have an example of what it would be in a real problem. So some of these we know, some of them we don't know. So top piece here, the multiplication property of exponents is if you have something a to the m times a to the n, you add the exponents. So in a real world or a real problem, if you have x cubed plus x to the 5th, you add up 3 and 5 and you get 8. Division property. You can cancel things from top and bottom. A to the m over a to the n is a to the m minus n. You subtract them, right? On the top spot here, we added, now we're subtracting. And to show why this works is if we have this x to the 6th over x to the 4th here, we have 1, 2, 3, 4, 5, 6, 1, 2, 3, 4 x's on bottom. You can cross these out, or you can cancel them. And we're left with 2 x's, which happens to be 6 minus 4. So we have our x squared. Right? That's why the division property works the way it does. The power property, or power of a power. Anytime you have an exponent, and then a parenthesis, and then another exponent, like what we have right here, exponent, parenthesis, exponent, you're going to multiply them. And let's show why that is. On the right here, we have x to the fifth, parentheses squared. This would be like x to the fifth times x to the fifth, right? We have it 2 times because it was squared, which you add those up and you get to the 10th. The zero property, anything to the zero is 1. All right, so anything to the zero is 1. If you have some big ugly problem on a homework where it's got a bunch of stuff in here, but then it's to the zero, it's going to be 1. All right, don't even worry about what's inside it. If it's to the zero, it's 1. The negative exponent property. We have a to the negative m is 1 over a to the m. And the way that I think about this is if we have like a to the negative m, I like to write that as a fraction. It's like over 1. The negative exponent means that it's not happy. It wants to be on the other side of the fraction bar. So we put it on the other side of the fraction bar, and then it's happy again. Similarly, if we had like 1 over b to the m to the negative m on bottom, that would be equal to b to the m over 1. All right, so it could either move from top to bottom or bottom to top, and that could be useful sometimes. Next up, we have power of a product property. So we have a times b all to the m. And this one, I kind of think of it as distributing. You distribute the m to the a and distribute it to the b. All right. In our real example over here, we have a times b squared, or quantity squared. Uh-oh, did I mess this up? Oh, no, I didn't. Okay, sorry. You distribute it there. And let me show you why that is. If we take this, we have ab squared. The squared means that we need to write it twice. So it's going to be ab, ab. And then we can drop our parentheses, ab, ab. So we have 2 a's, 2 b's, and there we are. It's kind of like distributing an exponent. Power of a quotient property means that if you have a fraction to an exponent, right, a over b to the m, you can kind of distribute that m, that exponent, to the top and to the bottom. So if we had 1 over 4 squared, you distribute the 2 to the 1 and to the 4. All right, let's look at some examples here. Number 2, simplify using properties of exponents and express with positive exponents, all right? Only positive exponents. X squared times x cubed, we're going to be able to add them there and get an x to the fifth. B squared to the third, we have an exponent, parenthesis, exponent. So that means we're going to multiply. So x to the sixth. X to the negative 3. Well, we can think about this as being x to the negative 3 over 1. That negative tells us that it wants to be on the other side of the fraction bar, so it's going to be 1 over x cubed. X to the 0, anything to the 0 is 1. No matter what it is, anything to the 0 is 1. E. This one here gets a little bit trickier, so we have the two things multiplied together in parentheses. So this 5 is going to kind of distribute to the x and to the y. So now we could write it as x squared. What do we have to do here? We have to write it as parentheses again to the fifth times y to the fifth. Now those parentheses there tell us that this is going to be x to the 2 times 5 times y to the fifth, which is x to the 10th, y to the fifth. F. Well, before we deal with this square out here, Let's simplify what's inside our fractions. We have an a and then 3a, or a cubed, so this will be a to the fourth b. Now, just like in the last one, I'm going to send this 2 to both of these. So this will be a to the, well, this is going to be 4 times 2, which is going to be 8, and then b squared. Right. I skipped the step where I wrote it as parenthesis in that one. G. Well, let's start off by putting this x with this x. So this is going to be 2x squared y to the 6th times x cubed y to the 4th to the 6th. Now I'm going to kind of distribute that exponent. It's not really distributing, but that's the way that I think of it. So this will be 2x squared y to the 6th times x to the 3 times 6. So what is that going to be? Is that 18? Yeah, 18. And then y to the 4 times 6, which will be 24. Now I just add my exponents, so I have a constant 2 out front, and then x to the 2 and 18 give me 20, y to the 6 and 24 give me 30. For h, I'm going to have to distribute this exponent twice, this one to here and that one to there. So this will be negative 2 cubed. A to the 6 times 3 is 18 times a to the 25. Negative 2 cubed is going to be negative 8. A to the 18. Actually, I could add those exponents together. What is 18 and 25? I'm going to type that in just to make sure. 18 plus 25 is 43. And there we are. All right. Make sure that we have these exponent rules near us. They can be very useful. And make sure we have this chart near us. All right. Good luck on the homework.